Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And salam sejahtera. Welcome back, guys. Okay, today topic we still continue with the chapter number 5, refrigerant cycle, part D. So, firstly, I would like to make the acknowledgement and thank you to Dr. Azmi Hussein for his efforts to come out with a nice and beautiful slide of this chapter, refrigerant cycle. Okay, let's continue with the objective for today class. Okay, the objective for today is number one. I would discuss or will review, okay, review the factor involved in selecting the right refrigerant for an applications. Okay, that is number one. Number two, you must be able to know, okay, or to evaluate the performance of innovative vapor compressions refrigeration systems. Okay, there are three modifications that we will see and learn on this subtopic of innovative vapor compressions refrigeration system. That is, number one is a cascade refrigeration system. Number two is about multi-stage compressions refrigerant system. And number three is about introductions or the concepts of absorption refrigeration system. Okay, these are all the objectives that you should able to gain after this class. When you want to design, okay, when you want to design the refrigeration system, there are several refrigerants which you must choose. Okay, that's mean before you want to do the designations of the refrigerations, several, as I said, several refrigerants may be used in refrigeration system. Okay, this is all listed what have been used, refrigerants that has been used previously in refrigeration system. Number one, we can use chlorofluorocarbons, that means CFCs. We also can use ammonia. We also can use hydrocarbons, that's mean propane, ethane, ethylene, and etc. Refrigerants also can use carbon dioxide. Air, that's mean in the air conditioners of the aircraft. Okay, we take the atmosphere air, and water. Okay, in the applications above the freezing point. Okay, when you read books, the history of refrigerants, you will find that ethylene ether. Okay, ethylene ether was the first commercially used refrigerant in a vapor compression system. That's mean in 1850. Okay, all of these refrigerants that I mentioned actually have the pro and cons. Okay, actually, ammonia. Okay, we look on the ammonia. Example of the ammonia. Ammonia actually the commercially used for industrial. So it is because of the low cost, higher. It have also higher coefficients of performance and good heat transfer coefficients. But ammonia is a toxic. Okay, uh, same as sulfur dioxide, ethylene chloride. That means also toxic. And then CFC, fluorine, also low cost, and R11 been used for the chiller, R12 fridge, R22 commercial buildings, R502 been used in a supermarket, and these all refrigerants if affect ozone. Okay, will affect the ozone. So now to replace this R12, uh, the government has required to use R134A, okay, which R12 will damage ozone layer in middle 1970. So R134A is used in domestic refrigerators and also freezers, as well as automotive air conditioner. So that's why if you look previously, the questions based on the refrigerants or the working fluid used refrigerants R134A. Okay, this is for the safety purpose. Okay, then what we have, okay, what we must consider when we select the when we want to select make a selections of refrigerant. Number one, actually the temperature. Okay, the temperature of the refrigerant. So what about the temperature? The temperature actually this is one of the important, okay, parameter need to be considered, um, because the temperature deal with two medium. Okay, this temperature will deal with two medium. Number one, it will deal at the refrigerant space. Okay, and also at the environment space. Okay, that is one of the parameters that important you have to consider. So the temperature difference between 5 to 10 degrees Celsius for reasonable heat transfer rate. Example, as you see here, to maintain the refrigerant space at 5 degrees Celsius, what you have to do, the temperature of the refrigerant should be around negative 5 degrees Celsius. So the pressure in the refrigerant cycle must be maintained slightly higher than atmosphere pressure to prevent any air leakage into the system. So the another considerations that can be considered is safe and non-toxic. So the refrigerants must be non-toxic, non-chlorophyll, chemical stables, and also non-flammable. Okay, and the important thing and other considerations is also it is must be available at low cost. innovative vapor compression refrigeration system. Number one is a cascade refrigeration system. As we discussed earlier, the simple vapor compression refrigeration cycle is the most widely used refrigeration cycle, and it is adequate for most refrigeration applications. These ordinary vapor compression refrigeration systems are simple, inexpensive, reliable, and practically maintenance free. But when we talk about large industrial applications, efficiency, it is not simplicity, and this is a major concern. For some applications, the simple vapor compression refrigeration cycle is inadequate and needs to be modified. So, one of the modifications and refinements can be done is by cascade refrigeration system. Okay, as you see in these figures, the schematic diagram of the cascade refrigeration system, and at the right side is a TS diagram of this cycles system. Okay, as you see, uh, due to the large temperature difference and to avoid a large single vapor compressions, modifications for two or more refrigeration systems are needed. Usually, this system use counterflow heat exchanger in the middle, act as a evaporator for the topping cycle, that means at cycle A, and the condenser for bottoming cycle, that means at the cycle B. Through the ratio of the mass, flow rates must be calculated. Okay, so here it has cycle A and cycle B. Okay, this is schematic diagram for the cascade refrigeration system, where at the middles it is uh, put as a heat exchanger. Okay, at the cycle B is considered as the condenser, and at the cycle A it considered as a evaporator. So to do the calculations for these mass flow rates, we know that at a cycle A, mass flow rate A times enthalpy 5 minus entropy 8, that's mean number 5 minus number 8 is equals to mass of cycle B times the difference of enthalpy 2 minus entropy H. And entropy 2 minus entropy 3. So 2 minus 3. And from there, we can get the calculations of the ratio of the mass flow rates is equals to H2 minus H3 divided by H5 minus H8. Okay, this is a formula to calculate the ratio of the mass flow rates for cascade refrigeration system. And as a result, to find the coefficients of performance for this refrigeration system of a cascade, the normal or the basic formula QL minus QL over W in net is equals to, okay, where QL is equals to M B times H1 minus H4 divided by the total of cycle A of mass flow rates and also cycle B. That means HA time H6 minus H5 plus M at cycle B, H2 minus H1. This is the formula that you can calculate or you can use to find the coefficients of performance for cascade refrigeration system. Okay, let's see the example. Okay, the example of this system. Consider a two-stage cascade refrigeration system operating between the pressure limits of 0.8 and 0.14 megapascal. Each stage operates on the ideal vapor compression refrigeration system cycle with refrigerant 134A as a working fluid. Heat rejection from the lower cycle to the upper cycle takes place in an elevated counterflow heat exchanger, where both streams enter at about 0.32 megapascal. If the mass flow rate of the refrigerant through the upper cycle is 0.05 kilogram per second, determine A, the mass flow rate of the refrigerant through the lower cycle, B, the rate of heat removal from the refrigerant space and the power input to the compressor, and C, the coefficients of performance of this cascade refrigerator. Okay, to do this, to solve this question, firstly, as usually, you have to draw the TS diagram, and also you have to understand basically on the schematic diagram of this cascade refrigeration system. So this system operates between two pressure, that means 0.14 megapascal and also 0.8 megapascal. Okay, and it have two cycles, cycle A and cycle B. And from here, all the states 1 to state number 7 has been defined. Okay, has been defined based on what has been given um, previously. Okay, and then it said this cycle using the ideal vapor compression refrigerant system. Okay, as you see here, it operates on the ideal vapor compression refrigerant cycle with refrigerant 134A. Okay, so we get all the enthalpies enthalpies, state 1, state 2 until state 7. Okay, as I said just now, based on the previous example. Okay, so you have to find all the enthalpies. From there, the mass flow rates of the refrigeration, the mass flow rate of the refrigerant through the lower cycle is determined. That means from the steady flow energy equation balance, SFEE, on the adiabatic heat exchanger. So we know the basic theoretical of thermodynamic second law in open volume system, where the rate of energy out is equals to the rate of energy in. So from there, this is the formula that I had mentioned earlier, this one. Okay, where the ratio of mass flow rate can be used. So we take out that formula, and from there, put all the values, m dot a at cycle A, also H5, H8, okay, and then m dot of cycle B, we want to determine. So H2, H3, we have find earlier. So from there, we have got m dot B is equals to 0.039 kilogram per second. For B, we want to find the rate of removal by these cascade cycles is the rate of heat absorptions in the evaporator of the lower stage. The power input to the cascade cycle is the sum of the power input to all of the compressors. So we also know the Q dot low is equals to M dot B cycle B time H1 minus H4. Okay, let's look on the TS diagram and schematic diagram at B. Okay, so QL is at process 1 and 4. That's mean at the evaporator. Okay, this is QL. So you want to find this QL using the steady flow energy equations for the device of evaporator. So from there, put thing the value of m dot b and also enthalpy 1 and also enthalpy at state 4, you will get q dot l is equal to 7.18 kilowatt. So the w dot in, that's mean in here w dot in this case w dot in, it have cycle A and cycle B, and it also have two compressors. So work rate W dot compressor in plus uh, work dot compressor number 2. So this compressor is M dot A H6 minus H5, and for cycle B M dot B H2 minus H1. Then putting the values in these equations, lastly you will get W dot in for the total cycles is 1.61 kilowatt. So using the COP or coefficients of performance for these cascade refrigeration cycles or system, Q dot L over W dot net in. So you will get the COP for this refrigerations cascade is 4.46. Okay, so as the comparison example earlier, that's mean 11.1 or example in ideal vapor compressions refrigeration cycle without modified for the single stage refrigeration system. What we noticed here, the COP for the refrigeration system increased from 3.97, that means from the earlier first stage without modified, to 4.46, okay, as a result of cascading. Okay, so the COP of the system can be increased. Okay, the conclusion that we can say here, the COP of the system can be increased even more by increasing the number of cascade stages. This is only one stage. Okay, so if you want to get the more increase in COP, so you can use a multi-stages of cascade system. So this is one of the modifications for the uh, innovative vapor compression refrigeration system. Okay, for number 2, modifications that can be done for this vapor compressions refrigeration system is by using the multi-stage compressions refrigeration system. But for multi-stage compressions refrigeration system, uh, so when the fluid, okay, used throughout the cascade refrigeration system is the same, The heat exchanger between the stages can be replaced by a mixing chamber. This mixing chamber is called as a flash chamber, since it has better heat transfer characteristics. So this is why this system are called as a multi-stage compression refrigeration systems. So as you see in the schematic diagram, this is a two-stage compressed refrigeration system. Okay. In this system, what happened? The liquid refrigerant expand in the phase in the first expansion valve to the flash chamber pressure, which is the same as the compressor interstate pressure. So the part of the liquid vaporized during this process. So the saturated vapor, that means at state number 3, okay, at state number 3, is mixed with the superheated vapor from the low pressure compressor. That means at state number 2. Okay, so at state number 2 and state number 3 will mix, and the mixture enter the high pressure compressor at state 4. Okay, in this, it is a regeneration process. The saturated liquid at state number 7 expand, okay, through the second expansion valve into the evaporator. Okay, where it picked up heat from the refrigerant space. The compression process, that means in this system, resembles a two-stage compressions with intercooling, and the compressor work decrease. That's, care should be exercised in the interpretations of the area on the TS diagram. In this case, since the mass flow rates are different in different parts of the cycle. So when the same fluid throughout the cascade system, okay, so the heat exchanger between the stage can be replaced by mixing chamber, okay. So this is what I had explained just now, okay. So the important, you have to know that the refrigerants expand at first expansion valve, enter the flash chamber. Part of the liquid vaporized during this process then will be emitted at the superheated vapor exit from the low pressure compressor, enter the high pressure compressor. That means this is the important point that you have to remember and understand. That means from state number 2, state number 3, it will mix at this superheated region, and then come from the low compressions compressor, okay, and then it will goes to the second compressor, high pressure compressor. Okay, let's look the example of this case. Consider a two-stage compression refrigeration system operating between the pressure limit of 0.8 and 0.14 megapascal. The working fluid is refrigerant 134A. The refrigerant leaves the condenser as a saturated liquid. Okay, this is a point that you have to know, and is throttled to the flash chamber operating at 0.32 megapascal. So when it said flash chamber, that means this question, it used the multi-stages refrigerant system. Part of the refrigerant evaporates during this flashing process, and this vapor is mixed with the refrigerant leaving the low pressure compressor. The mixture is then compressed to the condenser pressure by the high pressure compressor. The liquid in the flash chamber is throttled to the evaporator pressure and cool the refrigerant space as it is vaporized in the evaporator. Assuming the refrigerant leave the evaporator as a saturated vapor and both compressors are isentropic, determine the fractions of the refrigerant that evaporates as it is throttled to the flash chamber. Number two, the amount of heat removed from the refrigerant space and the compressor work per unit mass of refrigerant flowing through the condenser. And lastly, the coefficients of performance of this system. Okay, to solve this problem, you have to define first whether which one system is this. Okay, as I said, you have to know when it said flush chamber, this is a multi-stages compression refrigerant system. So this is the schematic diagram of the multi-stage compression refrigerant system, and this is a TS diagram for this system. So all the enthalpies you can you must define, or you have to find it using properties table, and I think at all stages has mentions the properties, that means pressure and also the temperature. From there you will get the enthalpy at each of stages one by one. Okay, number one, number two, number four, number four, number five, number seven, okay, number 8, 6, and etc. Okay, from here then to find the fractions of the refrigerant that evaporates as it is throttled to the flash chamber is simplified by the quantity at state number 6. Okay, which is, okay, we go at TS diagram at state number 6. We know that at state number 6, H6 is 95.47 kilojoule per kilogram. So using the quantity, okay, quantity X, because this state number 6 is is in the mixture region, so you have to find the quantity or the fractions of state number 6. So using this equation, H6 is equals to H is F plus HFG. Okay, sorry. I repeat, H6 is equals to X6 HFG plus HF. Okay, so from here you restructure these equations, then you will get fraction 6 0.2049. For B, the amount of heat removed from the refrigerant space and the compressed work input per unit mass of the refrigerant flowing through the condenser are so QL, okay, QL is equals to 1 minus X6 time H1 minus H8, okay. So heat removed from the refrigerant space, that means H1 and H8, okay, go back to the TS diagram. H1 and H8, this is at the evaporator. That means cool, this is refrigerant space. So QL, so you want to find in this device, okay. So QL is equal 1 minus H6. So H6, you know the fractions. one is 100% fraction, so put all the H1 and H6, then you will get the answer of heat, specific heat, QL is equal to 146.3 kilojoule per kg. And the compression work input per unit mass of refrigerant to the condenser are, so work in here it have two compressors, so you have to find each of them. For compressor number 1 is 1 minus fraction 6 times H2 minus H1 plus H1, that means 100% of the fluid go into the second compressor, H4 and H9. So we see H4 and H9 is 100% fluid, okay, but in bottom or lower cycles, it has a percentage, not 100%, okay. So that's why you have to do the minus 1 minus the fractions that go in this cycle. So put all the values in to know the work in, okay, but you don't know the amount of H9. So what you have to do, the enthalpy at state 9 is determined from the energy balance of the mixture chamber. So let's go look at H9, that means at state number 9, okay, H9. H9 is 299.1. Sorry, 255.1. So to get this 255.1, what you have to do, you know that the energy balance of this mixture chamber, that means specific using the SFEE, steady flow energy equations, E dot out is equals to the E dot in. So at E dot out is 100% fluid time the enthalpy at 9 is equals to the fractions of the fluid at H3 and H2. So H3 and H2, this is a mixture fractions. So H6 times H3 plus 1 minus H6 times H2. So from there you will get H9, put all the values that you know based on the above equations, then you will get H9 is 255.1 kilojoule per kilogram. So also S9 is equals to 0.9416 kilojoule per kilogram Kelvin. Two, we also know enthalpy at state number 4, that means 0.8 megapascal. S4 is equals to S9. S4 is equals to SG. So H4 is equal to 274.48 kilojoule per kg. So substituting all this value into the equations of work, then you will get the total work for these two compressors is 32.71 kilojoule per kg. So you have calculate QL and also W in total, so you can find the COP for this multi-stages compression refrigeration system using the basic formula QL over W in, because small q and small w, this is a specific heat and also specific specific work. So the unit is per kg. So from here it can be determined these two units. So substituting all the values in these equations, then we will get the COP for this system is 4.47. If we look using this multi-stage compression refrigeration system compared with the idea or single vapor compression refrigerant system, it have increased, okay, from same as earlier examples, 3.7, 3.97 from single stage to 4.47. Okay, this is increase when you made the modifications for the single vapor compression system. Number three of modification is using the, or it's called, its name as a absorption refrigeration system. This is another form of refrigeration that becomes economical, attractive when there is a source of inexpensive thermal energy at the temperature of 100 to 2 degrees Celsius. It free energy. Okay, some examples that come from the inexpensive thermal energy sources, including geothermal energy, solar energy, waste heat from cogenerations or process steam plants, or even natural gas where it is available in or at a relative low price. So the name of this absorption refrigeration system involve the absorptions of a refrigerant by a transport medium. Okay, so the most widely used absorption refrigeration system is the example ammonia water system, where ammonia serve as the refrigerant and water as a transport medium. Another example of absorption refrigeration system include water lithium bromide and water lithium chloride system, where water serves as a refrigerant. So this is a ammonia absorption refrigerant system. Okay, so as you look in this figure, what happened? This the dot line. This is replacement of the compressor. So that means we take the free or the inexpensive resource energy. Example here as from the solar energy. So from here we use this energy and then convert this energy into something that can be used, okay, as the functions as a compressor. Okay, so the system almost same as the refrigeration, except the compressor section seem more complicated. Okay, this is disadvantage. Consists an absorber, a generator, a pump, a regenerator, a valve, and also a rectifier. So when you look the vapor absorption process inside the box, what it mean by the box? Okay, this is the dot line in the box. Okay, here it shows generator, rectifier, regenerator, absorber, expansion valve, pump, and etc. So the process inside the box, what happened? Ammonia vapor leave the evaporator and enter the absorptions to form NH3 H2O. Okay, this named as the ammonia. The absorber needs to maintain cool in order to maximize ammonia dissolved in water. Then this ammonia will pump to the generator. In the generator, heat is transferred from the vapor source, that means solar heat. Then this vapor will pass through the rectifier, which is separate the water. The high pressure pure ammonia continue through the rest of the refrigerant cycles. So the hot ammonia plus water solutions which weak in ammonia then pass to the generator. Heat is transferred to the rich ammonia solution from the pump. And finally, the remaining of hot ammonia plus the water solution is throttled back to the absorber pressure. So the advantage of this absorption refrigeration system is work input to the absorber relatively small. Okay, so this advantage, it is expensive, more complex, space consumed, required large cooling tower to discharge heat. So um, even though we have the free sources, okay, free sources for can be used, free sources of energy that can be used to process this system, but we need more complex structure, more devices we have to design, and all these devices that we design only use as the same as the purpose of compressor. So that is a disadvantage. So the absorption refrigeration system are much more expensive than the vapor compression refrigeration system. They are more complex. Uh, they are more complex and occupy more space, as I mentioned, and therefore absorption refrigeration system should be considered only when the unit cost of thermal energy uh, is low and is uh, projected to remain low relative to electricity. Absorption refrigeration systems are primarily used in the large commercial and industrial installations. However, if you want to calculate or if you want to make the analysis of this absorption refrigeration system, the coefficients of performance for this system can be calculated based on the basic equation desired output per required input. So you can find QL, that means heat at low, over Q generations, where the heat that regenerate in uh, the design absorption devices plus work in pump. Okay, is equals to QL over Q generations. So by assuming all the process is reversible, the maximum COP will generate. This possible by Q generation will transfer to the Carnot heat engines and work output supplied to the Carnot refrigerations. So to find the output work, you can use the efficiency of thermal heat refrigeration time heat generator. Okay, and QL can be found by work time COP refrigerant reverse, okay, reversible process. So it's equals to thermal efficiency reversible time Q generations times COP regenerations for this refrigeration. So the COP for these refrigerations absorptions using this formula and simplify all these formula, then you will get 1 minus TO over TS time TL over TO over TS. What is TO? What is TS? Okay, we refer from this. Okay. refer from T. O is T at state where TO is temperature at the environment. TS the temperature at the source. Okay, the source. TL is the temperature at the refrigerant space. And okay, all these TOTL you can refer to chapter 11 in Chengel's books, thermodynamics, in figure 1124. Okay, so this is how the explanation or introductions about the absorptions refrigeration system. Okay, next is the properties table, quality adds. Okay, this is just the for the recall back your memory in thermodynamics. Okay, I just go through. I'm not explaining anything about this. I just go through. So this is note in thermodynamics. Okay, TV diagram, PV diagram. So you have to know the saturated line, saturated critical point, etc. So please read back or see again your properties tables, also your notes in thermodynamics. Okay, this is how you calculate the quality adds or fractions. Okay, quality adds. What is this? What is quality adds or fractions adds? Okay, so I think that's it for today, for this time. So we have completed chapter number 5, refrigerant cycles. Okay, the objective has been introduced, or should be able to know after I have completed this. You should be able to know the considerations when you want to do the design of the refrigerations. And also you also should be know the modifications that can be made, and also the calculation and analysis that can be calculated based on the modified refrigeration system. Okay, 3 modifications can be done for the single vapor compression refrigerant system. That means the first one is gas refrigeration system. Number 2, you can do the multi-stage compression refrigerant system. And number 3, maybe you can modify based on the absorptions compressions refrigeration system. Okay, that's all guys for this time completed chapter number 5. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh dan salam sejahtera.